This is going to be Chapter 9, Differential Equations, and we're going to be looking at 9.1, 9.3, and 9.4. So it is a shorter chapter, and you'll kind of see a little bit more of differential equations if you take Math 255. But here you're just going to get a little taste of how to do some of the basics, especially also what is the differential equation definition. So basically, differential equation, we call it either a dpq or a dE. So a differential equation, let's just write a dE. It's basically going to be an equation with its own derivatives. Okay, so usually what happens with a differential equation is that you don't really know what the function is. The function is a known, but you know how to find or combine the function with its own derivatives. And sometimes they look kind of like this. So a differential equation may look like y double prime plus y prime plus y plus 7 is equal to 0. So if you have it in this notation, you can see it like that, or you can also have it in this other notation as well, so Leibniz or Newton notation. So you can have something that looks like this too. So you have many different types of differential equations. They contain their own derivatives. Sometimes they're used in population growth. Sometimes if you have like predators in some sort of like colony, it might be you might have a difference in the population if there's predators as opposed to there's no predators, or nutrition, or if there's some sort of disease going on, obviously the population is going to go down. So differential equations can help you do that. You can model it with that. So, and the whole point about differential equations is that you want to be able to find the function. So the goal of differential equations is we need to find the original function. Okay, so that's the whole point of it. Okay, so so what we're going to say is here that a function f of x is considered a solution to a differential equation if the equation and its derivatives are substituted into the equation. Okay, so it's going to be very different now, because usually we're so used to having some sort of equation we solve for x, and then all you have to do is plug in x back into the equation, and then you'll get your answer. But now in this case, you want to find a function, and the function and its derivatives, if you plug it back into the differential equation, you'll just get the solution, or it should equal, that both sides should equal. So let's just do a quick example of what this kind of looks like. So let's say we want to show that y equals e to the negative 2x satisfies the differential equation y prime plus 2y equals 0. Okay, so this is what we want to show. Okay, so what you really want to do with this problem, the first thing is that you want to make sure that this is actually the answer. So they've actually figured out what the answer should be, y equals e to the negative 2x. So now what you got to do is just basically plug it in and show that it actually is a solution. So the first thing that you want to do is, we know that y equals e to the negative 2x, so we can plug that in for this guy. Now what we need to figure out is what is going to be the derivatives, so y prime. So the derivative of this, well, this is just by the chain rule, it's going to be negative 2 e to the negative 2x. So all we had to do is just plug these guys in their respective y prime and y. So this guy's going to be negative 2 e to the negative 2x plus, and then you have a 2 here. And then I'm going to multiply this by y, which is e to the negative 2x. And is this equal to 0? Well, yes it is, because negative 2 e to the negative 2x plus 2 e to the negative 2x indeed equals 0, since these guys cancel out. Okay, so therefore this is actually a solution. Okay, now this was very basic because they were already given to you, the solution was already given to you. Now, how do you actually solve for one? How do you find the solution of a differential equation? So, so how to solve a differential equation? Okay, so the way that we kind of do it, we're gonna talk about something called separation of variables. Okay, and the whole thing about separation of variables is the following thing. So a separable equation okay, I'm going to underline that, is a first order differential equation in which the expression for dy over dx can be factored as a function of x times a function of y. Okay, so that's what a separable equation is. So a separable equation is a first order differential equation in which the expression for dy over dx can be factored as a function of x times a function of y. So what I mean by first order, and I think I didn't really quite explain this, first order differential equation just basically means that you basically only have one derivative. So y prime plus 3y equals, I don't know, it could be sine of x. Okay, that's a first order differential equation. Second order means that the differential equation has a second derivative. So like y double prime plus cosine of x, y plus blah, 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 blah. Okay, that will be a second order. And so on, you can have more different orders. So basically what it means is that a separable equation is going to be a function that has a derivative, so it's first order, so it has dy over dx, and this equals a function of x multiplied by a function of y, okay? So this is using this notation, but you can always have it as y prime equals g of x times f of y. So if you know that this guy can be broken up like this, then you can go ahead and use separation of variables. And what basically separation of variables does is that you can break up this operator so that I only have x's on one side and y's on the other side. So for example, if I have dy over dx is equal to g of x f of y, then what I can do is that I can move the dx over by multiplying by dx. So I'm going to have dy is equal to g of x, f of y, and then I have the dx over here. And then I'm going to move the y over. So I'm going to divide here by f of y. This is going to go away. So I have 1 over f of y dy equals g of x dx. Okay, and basically what I've done is that I put all of my y's together and I put all of my x's together. And the whole point of separation of variables is that now what I can do is I can integrate both sides. Okay, so if I integrate both sides, I will be able to get rid of this dy and this dx by just taking the antiderivative of these functions, okay, assuming that they're integrable. And even if they're not integrable, you can use maybe something else. But and then after that, just solving for y, because notice that once I have this, you'll have some sort of y, okay, and that you can just go ahead and solve for on the other side. Okay, so that's basically the basics of what we're going to do with separation of variables. So in the next video, we're going to go ahead and do some examples of how do we use separation of variables and how do we solve for them.